In terms of the introduction, I'll just flesh out a little bit. Yeah, thank you so much for having me here. I am finishing my third year of PhD. I've been studying this stuff for the past 3 years, mostly because at IBM I was sitting at snack time with Dima, and he pulled out a napkin. Dmitry Krotov, whose name I'll mention a lot in this talk because his work is fundamental and foundational to almost everything that I've done and that we've done together. And he pulled out a napkin and a pen and essentially sold me on his elegant vision for what AI could be. And I hope to share a little bit of that with you all, whoever's on this call today in this short presentation. I also want to mention, if at any point people want to ask questions, feel free to ask away and interrupt me. I will stop once in the middle of my talk and accept questions, and of course there will be questions at the end. So before we dive in to associative memories, Hopfield networks in general, it's probably good to build a little bit of an intuition. What is associative memory? What is this thing called memory recall? Well, we all kind of are familiar with this already because essentially brains are associative memories. So a little bit of a personal anecdote. Growing up, my mom is a baker, and every morning at 5 a.m. she would wake up and you know, her bakery was set up in the house, and she would start baking. So I would wake up almost every morning to the smell of you know, almond biscotti, let's say, probably her best-selling item. To this day, I can smell almond biscotti or almond extract of any kind, and I can remember arbitrary days from my childhood, just randomly, like what it's like to wake up. And that's completely involuntary. My brain makes that connection for me. These two very disparate things, the smell, these chemicals in the air, and screenshots of my youth. They're connected in my brain, and one can be retrieved by the other. This is the idea of associative memory, where very disparate, different kinds of patterns and data can be stored together and connected such that presenting one can retrieve the other. Perhaps you have similar stories in your life. Another interpretation of associative memory in the brain, this idea of error correction. So brains are, you know, associative memories, and we're really good at getting things right when we're presented with something close enough. Here's probably my favorite example. According to a research study at Cambridge University, it doesn't matter what order the letters in a word are. The only important thing is that the first and last letters be at the right place, and so on and so forth. Brains are incredibly good at this task, right? These words are gibberish. There is no such word as rod or olni or any of this. If these misspellings don't seem to interfere with my ability, or perhaps even anyone here's ability, to understand what the message is, these very noisy words are quickly condensed and interpreted in my brain almost without me having to think about it. So this is one other attribute of associative memories that I think is very powerful, is we can be presented with nonsensical, noisy data. So long as it's close enough, we can converge to the right answer. So how do we encode this concept of associative memory that I've described biologically, or not even biologically, just intuitively, in math? Well, to do that, associative memories like the Hopfield Network are a form of energy-based modeling. So we need to understand what energy is and means in the context of data science and in AI today in order to understand what these models are actually doing. So energy, this concept of energy, is in data science fundamentally linked to the concept of probability. That is, there's actually an equation that equates them, and that's called the Boltzmann distribution equation, where the probability of some piece of data, some event y, is equal to the energy in the exponent and modified by some inverse temperature beta, divided by some normalization constant z to make sure that all of your energies are sum up to 1. So in a sense, energy is a little bit like unnormalized probability, or more precisely, energy is proportional to the negative log probability. It's a good way to kind of interpret what's going on there. And so here's a little bit of a graph, right? So probability on the top. What we care about is learning probability distributions. That's what AI cares about. We want to know, given all of the possible data out there, what is meaningful data, what is not meaningful data. And when it's come time to use these models, I want to sample from the regions of high probability, because this is what represents meaningful data. Of course, I'm not going to use the word probability much more in this talk. I'm going to switch to talking about energies. So when we say we're trying to find peaks in probability, another way of saying that is we're trying to find the valleys in the energy, or the minima of energy. So the task of associative memory, or these energy-based models, in general, of which there are many, is to turn data to sample from these regions of low energy, because these regions of low energy correspond to real-looking data. Formally, we can define it and work with this in this talk. Energy-based models are functions. These functions are typically learnable by a set of parameters that assign to every possible data point a scalar energy. The lower that energy, the more likely that data. For instance, take these two images side by side. One is a picture of a parrot. Your brain will recognize it as a parrot. The other one, your brain will probably still recognize as a parrot because, as we talked about, brains are pretty good at error correction. But it is not a parrot because 50% of this image has been blocked, has been occluded by gray squares. Now, say we have an energy function, right? The energy function will take as input these images and will spit out a prediction for the energy. The real-looking image, provided that the energy function has been trained well, will return a low value of energy. That's a very likely image. This pixelated, occluded image that it's never seen in a training data set, it will say, hey, that's not quite right. I've not seen that before. I've not been told to learn that. It will spit out a higher energy. And the problem of energy-based models, the task, one of the ways you can apply it, right, is how do I go from the corrupted image on the left into the real-looking image on the right? This is the problem of sampling. And it is not within the scope of this talk, but in general, sampling from EBMs, energy-based models, is difficult. It would be a lot easier if we could guarantee that the energy function that we're trying to sample from is differentiable everywhere. What that means is, smooth, continuous everywhere. What does that give us? How is that useful? Well, consider that noisy parrot from the previous slide. I'm pass it to my energy function. I can compute both an energy value and a gradient, which will tell me which direction I should go to maximally decrease my energy, or again, in terms of probability, to maximally increase my probability. Great, so if it's differentiable everywhere, I can just follow the gradient down and eventually converge to some really high probability, low energy image. One other issue. If we do that without putting any constraints that the energy is bounded from below, what's stopping our energy function from having values at negative infinity? This is not only not a well-behaved system from a dynamical system point of view, which is certainly of interest to those studying neurons in the brain and memory in general, it's also means that the energy function just doesn't have much meaning, right? Because the probabilities aren't smooth. We don't know where the meaningful data actually lives. So here's an example. What does a very simple example of a differentiable everywhere and bounded from below energy look like? This little snippet is quadratic. It looks a little bit like a quadratic function where the noisy parrot lives at high energy and the very clean looking parrot lives at low energy. We could go, assuming points 1 and 2, from the noisy corrupted to the clean parrot using gradient descent because we have those conditions in place and we know that we will converge. And if this is the case, then the energy function that we have has a special name, and that special name is called Lyapunov. And Lyapunov functions have this really interesting thing where, when we do gradient descent, which is defined as an operation through time, we can guarantee that the energy will decrease. So we're always going to improve what our image looks like. In fact, if we have these requirements, this particular energy-based model, we can define it using another word, and that's the title of this talk, because this is an associative memory. And in the language of associative memory, the corrupted input here converges to something that lives at a local energy minimum. And that minimum is called a memory. Memories live at local minima of the energy landscape. The question that really fascinated John Hopfield, I'm sure, in the 1980s and many since, is how can neurons encode this behavior of associative memory? How can we mathematically encode this in a dynamical system? And so this is where we introduced the classical Hopfield Network, which was already introduced briefly in the introduction to my talk as having a huge effect on the field of AI. And certainly I don't know the full extent of its impact. But for this purpose of this talk, I'd like to summarize my perspective, the least that you need to know of the classical Hopfield Network. Fundamentally, the classical Hopfield Network is composed of two main things. The first is a set of synaptic weights. This is kind of like your memory storage. We're going to denote the synaptic weights as psi mu I. Also, we have a separate component called the neuron state. And it's a state because it evolves in time. And typically the neuron state will represent the corrupted data that we're trying to clean, right? So that's what the gradient descent is defined upon. For an example, I often like to use this concept of trying to store MNIST images. So on the left here, we have a 9, a 6, and a 4, and a 3. These MNIST images are turned into 784 dimensional vectors and literally inserted as rows of the synaptic weight matrix. Each row, we denote psi mu with bold font. That's a vector. And what's very interesting here is, right, this synaptic weight matrix everything has meaning. I know exactly where to pull out a vector, and I know how to visualize that because it is the data. The data is the computational block of the Hopfield network. So this is my memory bank. I've stored the things I want in it. Now I'm presented with, say, a noisy image of a 3, in this case, because I've stored MNIST images, I need to provide some form of an MNIST image to try to retrieve. And then we define an energy function on top of this, right? And the energy function is probably one of the simplest things you can come up with that will satisfy the criteria that we mentioned above of a Lyapunov energy function. It's a negative quadratic of the dot product between the psi matrix and the neuron state V. And of course, the dynamics we descend is sending the energy with respect to the neuron state itself, which in the form of the classical Hopfield network turns into something that looks like this. The actual math, I want to build an intuition for, because it's really not scary. In fact, what this inside the parentheses is happening on both sides is a dot product. I take my neuron state here, and I do a dot product with every row of the synaptic weight matrix. So now we're going to come up with an intuition. So that's all that's happening, really, inside of the energy function. I do a dot product, and I square the output of that dot product. Intuitively, what that means is the bigger values, the closer V is to psi, that is, the more it looks like it, a dot product in space is like a cosine similarity, the lower the energy value. That is, the lower energy values are the regions we're looking for. So what is the intuition of the Hopfield network? We're defining an energy function that behaves as we described earlier, such that intuitively we make our query, the neuron state, look like our keys, the rows that we've stored inside the synaptic weight matrix. That's the classical Hopfield network in a nutshell. Here's what it looks like, found a fun little animation online. Noisy butterfly turns into clean butterfly by descending the energy. Noisy butterfly lives at high energy. Noisy butterfly converges to clean butterfly that lives at an attractor or memory of the energy landscape. As Shakar mentioned early, also is classical Hopfield networks have a storage problem. That is, I'm going to do my best to explain here. If two of those rows in that synaptic weight matrix, two of those patterns that we've stored in the memory bank are too close together, they start to interfere. Now, rather than having our desired local minima on top of each of these patterns, we actually have them talking to each other such that a new local minima is created somewhere between them. That's a little bit like the average. When we put 100 MNIST images in that database, we desired that we could get 100 back out somehow. If we were close enough to each of those patterns, we should be able to retrieve it. But this is a feature of the classical Hopfield network that sometimes these memories talk to each other. And in fact, the storage capacity is incredibly low. This was solved in 2016 by Dima Krotov and John Hopfield himself on something they called a dense associative memory. And the intuition for that is as follows. We can actually make distinguishing basins. We can draw a little bump between them if we think of it like a little bit like a mixture of Gaussians. If there's a Gaussian over each of these stored memory patterns and we make them narrower, what happens is we actually get this desirable peaking, or I guess in energy terms, basoning, centered about each stored memory pattern. And this allows us to store many, many, many more memories. In fact, it's basically solving the small storage capacity that plagued the Hopfield network for almost 35 years. And this kind of started to usher in just a chain of things that we've been able to see associative memories do or perform. So dense associative memory, what is it? It is exactly the same as classical Hopfield network in terms of the fundamental components. You still have a synaptic weight matrix. Here, they still represent MNIST images. You still have a neuron state, which in this case still is a noisy 3. And then we're going to do something to this energy function. This was the classical Hopfield network energy, negative quadratic of the dot product. We're going to change it. What if we consider things that are not just quadratic? That's informed by this capital G here. This is a function that's going to turn this dot product between the neuron state and synaptic weights into something maybe that grows faster than squared. One thing that's considered is if you throw an exponential here with a low temperature, these memories will start to separate out and show that very peaky behavior. So this is the dense associative memory. It's just like the classical Hopfield network with one key realization. We can be very general about our choice for function g instead of a quadratic. Many of them will have the same properties of being bounded from below and convex and all this wonderful things. But some of them exhibit much, much better storage properties than the original. So I made a little demo. This was for the Associative Memory workshop at NeurIPS last year. You can actually scan this QR code and check it out for yourself. But I just want to highlight just a couple things because we're running a dense associative memory behind the scenes here. And the function g that we're using is the log sum x, essentially a form of the exponential. So it's very sharp, very peaky. And yet, one, is it's still very smooth. It is still very smooth, and you can still interpolate or do follow the dynamics from one image that's stored in the database to another. The setup here, I said that there's only two things that you need to know. What is the dynamic state, and what is the stuff that's stored in the memory bank? In this case, you can go here, and for the full description of the math, the memory bank is composed of these images. We've inserted faces of people that were speaking and organizing the workshop. And we've also put them next to the pixels of the representing the image, we put them next to a label, and that label is their name, such that when a person clicks on each of these names, the associative memory triggers, and it tries to retrieve the image corresponding to that name. This runs in JavaScript, but the interesting thing is the JavaScript is only doing one thing. It is only running that dynamical system at all time, which means I can just let it go, and it will just keep running because it converges each of these different faces of people that are speaking and organizing at the workshop. So that's what I wanted to emphasize with this. Feel free to play with it. You're not going to break anything on my servers if you try your best. That's the power of JavaScript. But again, dense associative memories aren't perfect, actually. Again, they're very simple, just like the classical Hopfield network. They are composed of synaptic weights and one dynamic state. What if we want to apply this to problems in, deep learning today? Say, for instance, you have a classification task on really large images, like ImageNet, that you can't just flatten out and store as a row or a column inside your synaptic weight matrix. What if we want to have hierarchy? Say where we have one matrix that's dedicated to learning local features that are very simple, like lines or circles. And say we want to make it simple for downstream matrices too, so that they can just learn to compose these features. They don't have to learn from the pixels from scratch. This is, of course, the power of deep convolutional networks, where they can learn their own features. And at the end, say we want to have class label prediction, right? But we don't want the class labels to talk to the features that are the local features, because we have a class label that's assigned to an image, not to patches of an image. And we don't really want to define a convolution on the entire image itself. That's a waste of computation. So we have these things separated by several orders, several deep learning layers per se. How do we do this? Well, it turns out that those very simple rules of defining an energy function, and that these very simple matrices and dynamic states can stack arbitrarily, such that we can have a dynamical system and an energy defined for this. We can have a dynamical and an energy system and an energy function defined for this, and we can have an energy function defined for these two. And that coupling all of these energies together produces a cohesive associative memory that is a Lyapunov function. This is something that Dima realized in 2021, building off of the Lagrangian framework for associative memories that he and John Hopfield published in 2020, that essentially says, hey, you know what? We can work with Lagrangians. And when we work with Lagrangians, all of these dependencies on variables kind of start to simplify. We don't need to take the derivative with respect to every other dynamic variable when we're just considering one of them. So we only need local energies to describe the whole dynamics. And when everything just needs local energies and you connect them arbitrarily in this thing called a hypergraph, that's probably my first dive into this field with Dima, trying to describe this structure of hierarchical associative memory in a way that you can encode into a computer. And we settled on the idea of a hypergraph alongside the powerful autograph structures that are in all the deep learning frameworks these days. So yes, I would love to talk more about the math that makes this possible, but I just want folks to have the following takeaways. Hierarchical associative memories give us all the power that we want. Like theoretically, right? We can now model deep networks with associative memories and energies. and they still behave just like the original Hopfield Network intense associative memory as a Lyapunov energy function. But now it has learnable hierarchical features, and those linear dot products that we talked about between the memory matrix and the neuron state, we now can use any arbitrary synaptic operation instead. So what does that look like? We can use convolutions. Sure, convolutions can belong in an associative memory. Pooling, yeah, there's some issues with zeroing out gradients when you just pick and choose the max, but we can do it. It fits the framework. Sure, you want a multi-layer MLP to describe a connection between a neuron state and itself? Yeah, why not? But also, we can think of something like attention. How does attention fit into the idea of associative memory? So this slide ends kind of me building the foundation for where I kind of entered into the field of associative memory, and how I started to see a lot of connections to the state-of-the-art architectures that we're using today. What are transformers and what are diffusion models fundamentally doing? So this is the first break, and actually the only break I have scheduled to take questions. I think the second half will fly a little bit faster, but perhaps be a little bit less technical. So are there any questions right now that I can answer?
I have a question.
Yes.
So you mentioned composing the sort of energy functions. Does that so I'm somewhat familiar with Hopfield networks, but I'm also familiar with Hebbian learning. And I found that when you try to compose a lot of local learning rules, they kind of I guess lose the plot. They tend to not compose too deeply. They tend to probably they're probably interfering with each other in some way. Do you have any thoughts on this? Have you do you know? Yeah, I don't know.
Oh, certainly I have thoughts. The question is whether I can express it in strong formality. So let me address that. Hopfield learning is a wonderful way to train standard Hopfield networks. The strength of connection gets bigger, I guess, for those that don't know. When two neurons are connected via a synaptic weight and one of them fires, the synaptic weight strengthens to indicate, these two things should be associated together. So now you're asking, okay, we have a bunch of layers connected together, and we're trying to train a bunch of these using Hopfield learning. Let's think intuitively what happens, right? So these orange dots, these are the synaptic weight matrices in these diagram, and these blue squares represent the neurons. Say we only have one, like in the case of a deep convolutional network, we present an image, and we want to learn this whole thing with Hopfield learning. Here's the thing, everything with a circle around it, with this arrow, that's a dynamic variable. So you have to initialize it somehow, right? And if we're trying to learn all of these weights, we don't actually have a good guess for what we should initialize this, because these features haven't been learned yet, these features haven't been learned yet, so what do we initialize this with? So we just take our best guess, maybe all zeros or noise or something. Now train with Hopfield learning. You have an image and noise. Hopfield learning tries to make these synaptic weights strengthen whenever noise fires and whenever original image pixels fire. Now, what about Hopfield learning here? Well, Hopfield learning is going to do nothing because it's just going to learn whatever you initialize a deeper neuron layer with. And here as well, right? You require that the way you've initialized when you do the Hopfield learning has something meaningful. Is that answer to here, the deep layers, but it's going to have to go through your lame, sad initializations for all of these other dynamic variables in the process.
Yes, that does answer my question. But wouldn't that apply to almost all local learning rules?
Yes, it would apply to all local learning rules, because of course information can only propagate from here deeper. What I described is a problem initially, but you can imagine, right? If this affects this and this is learned well, then the state that you start learning here will affect this in a meaningful way. So it should, propagate, at least in theory.
Thank you.
Yep. Of course. Other questions?
Yeah, I wanted to ask about, you sort of mentioned these basins of attraction. Is that something you can compute?
Can you clarify? Can I know all of them in advance?
Yeah, something because I know you can do sort of you can calculate the storage capacity, right? And so I was sort of wondering how much can you generalize that?
All right, I'm going to give you my best attempt at an answer here. I think that these energy functions can be incredibly complicated. And to know in advance where the fixed points are is very, possibly intractable, because that would basically be like saying I can have the whole distribution of all my data, I can just know it. And it's kind of the same reason why sampling from energy-based models is really hard, because without some structure imposed on the energy function, how do you know where the model has learned? It's like you have random network, deep network, like a transformer, and you want to know what the ideal parameter configurations are because they represent minimum in a giant loss function. The best way to find those is by doing some form of gradient descent from a starting gas. So yeah, no, the storage capacity, I don't actually know if I can talk too much about that. I don't know how it's calculated, but it assumes random binary patterns that you're storing. And so what you essentially do is you say, at some point, these two things will compete with each other. I'll have too high a density, and I won't know the exact one that I'm reaching for. So you to characterize storage capacity, you characterize how much the crosstalk is between these patterns, which doesn't require descending energy empirically.
Yeah, that makes sense. I was just because it was more like wondering about because there's a lot of like statistical mechanics calculations, and that was kind of more where my train of thought was.
Well, I would actually be very interested in talking more about the statistical mechanics calculation, because it is a statistical physics model. And as a computer scientist, and as you mentioned, with dabbling with biomedical engineering, electrical engineering, and biology stuff, I haven't yet done that statistical physics. But yeah, it's a perfectly valid perspective.
Wait, are you just talking about are these just OEDs that you're solving here?
Can you say that again?
Are these just OEDs that you're solving?
ODEs?
Yeah.
They yes, they're very simple. This is the equation this is the equation that we're solving. Yes.
Okay, so it's plausible that some of these OEDs that you might actually have to solve are intractable.
I'm not sure about that, actually. I wouldn't know how to answer that question.
Fair enough.
Yeah. Yeah, certainly there's many questions regarding these things that I am not qualified to answer yet. But there are many things that I try to make as easy to understand as possible, because that's the framework that I've, really benefited from making connections in, and that's the one I'm trying to communicate today. Are there more questions on kind of the history of Hopfield networks leading up to 2021? 2021.
Oh, it. Let me first say that I'm a huge fan of this architecture, and thank you for excellent presentation. I'd like to ask if so in like there's this hypothesis in neurodynamics about like attractor hopping between different kind of like states of the brain, and there is some connection like through like manifold hypothesis and etc. to that it stores representations. And so I wanted to ask, and like I understand this is an active area of research, but do you have any ideas on how to probe the internal like structure of representation, sort of like for lack of better term, like latent space in those associative memories to identify how something is represented?
Yeah, well, certainly I can always say ideas. Whether they're right or not, it's kind of up for empirical evaluation. It seems like your question is saying, hey, you know what? These things can learn really complicated structure, but what if that latent dimension actually has a relatively low dimensional manifold that all has meaning? How can we explore that? Is that correct?
Yes, exactly.
Okay. So what I've described so far, I think, in all of these things, the dense associative memory, the classical Hopfield network, is the idea that we're almost like point attractors, where a clean image is one point in that energy, in the input to the energy landscape, right? And we're trying to converge to what the clean image is. And then we say we have stored a bunch of memories in that, a bunch of images, and then we have a bunch of points that we converge to. So in this framework, it's actually difficult to see what is the learned manifold, right? If everything that we're converging to is just a point. There's a few things that I think can make it a little bit easier to see that we might have a manifold. So I might go back here and say this is one hypothesis, right? Please take it as an hypothesis. The competing memory issue, the low storage capacity of the classical Hopfield network, essentially said, I can have 2 points that, could be a point detractors on their own, or we can change the width of that basin such that they start to talk to each other and create almost a smoother energy function. So controlling the width around each of these basins of attraction would allow basins of attraction to talk to each other a little more, which, in the original Hopfield network is undesirable. But perhaps in exploring the manifold, it is desirable because as memories talk to each other, you start to see meaning in between the memories themselves. So that's my first hypothesis. How would you explore this? Is you start playing with temperatures. I say temperatures. You start playing with the spikiness, like how deep those basins are and how narrow those basins are. And when we start doing that, we might be able to start to see meaningful manifolds inside of the deep networks. Of course, in the small networks, I'm not sure. Like the single layer, single matrix networks, I'm not sure what we would see. And honestly, we haven't trained any of the big hierarchical ones yet to be able to explore. But again, all open research. Good question.
Thank you. Thank you. Does anyone have any other questions? If not, can I ask another one?
Please.
Please go.
Yeah, sorry. I don't know, my question is kind of on the convergence between the neuroscience, like biology, neurobiology, and the computer science as the neural networks, which is very interesting. Like what you told about the models forming memories, it is a sort of similar to how the biological structures work. And very interesting ethical questions arise if we start to talk about consciousness. Like, I know that it is logically irrelevant thing, but it is a ethically, morally relevant thing about it. Can we sort of talk about the models having an experience from the algorithm working? So, like, if we try to define the consciousness as the sort of algorithm working on the sort of as you explain it, like it's just a point in the between between future and past, and we just like the model is keep learning, and the similar can maybe happening inside a model. Like, is there a way of talking about experience of a model like this?
Oh wow! Oh, very philosophical. I can see what kinds of questions you think of, and
it is indeed philosophical. But the question is more like, can we approach it somehow in this?
So, yeah, let me try my best, but I won't spend too much time talking about consciousness. So,
yeah, sure, I understand.
Because one, I think in general, consciousness is very poorly understood or defined at all. And so, how do you define the experience, quote unquote, of a model? You've seen the math equations. That's all it's doing. Right?
Yeah.
I can tell you this model, all it's doing is it's trying to find the best data to retrieve at the bottom of an energy function. So you start ascribing words like consciousness and experience to this process of energy descent, and I'm like, you know what? When I just look at the math, that's really hard to empathize with. It's like, it's just numbers, right? But then you start to think, oh, wait, there is a connection maybe, right, to biology, and brains might be doing this. And if brains are doing this, then we've discovered, and this is all very aspirational, right? But if brains are doing this, then we've found the algorithm of the brain for what governs thought and memory and experience and consciousness. So then how do you define consciousness and experience in the form of like memory retrieval? I'm a little unsure about that. My best guess, right, is that our brains as associative memories are connected not just to the outside world, right? We have lots of internal sensors. We can feel our feelings. We can feel like our arm position or our leg position. We feel pain. All of these sensors kind of govern our perception of self. We can even put ourselves in someone else's shoes and imagine how they see us. And so what is consciousness if I had to define it in terms of associative memory, is like, okay, it is my best guess at what all of these things together mean. That's who I am. I am the middle of that. And that's just a philosophical question. That's the most I'm going to say about that.
Yeah.
Fun questions, though. Definitely for another time.
The question is more about, like, is it approachable from this side?
I still don't know what it is. Defining experience and consciousness is tricky.
Yeah.
So once we define that, then we can define whether it's approachable or not. Yeah.
The framework is kind of paradoxical itself, and it's not necessary to define it, but we as beings want to. That's the question, really. Thank you so much.
Yes. No. Thank you for your question. There was one more question. Virginia?
Oh, yeah. So I was just wondering about kind of, sorry, I don't know how to put this, but in for example, in frustrated random systems, where like Hopfield Network kind of takes inspiration from like the Ising model, Potts model, etc. There is sometimes like a frustrated ground state, and especially in spin glasses, there is like this whole kind of like basic like flat valleys of energy of lowest energy in there. Is like, does this ever happen in Hopfield like in these Hopfield models, or like 2.0, or does it?
Yeah. 100. So these are still technically Ising models. They're just much more complicated Ising models, which means that the Ising model issue of running into spin glass states or metastable states where it looks like you're in a flat energy valley for a long time, but if you wait long enough, eventually you realize, oh, there's actually a better region over there, and you start converging to that. Totally still happens. It's still just a very complicated Ising model. Yeah, it still happens.
Thank you so much. Thank you. I'd love to talk more with you about this sometime in the future.
Of course, please. In the interest of time, I will probably move on and take whatever remaining questions there are at the end. That's okay with people? All right, cool. Because I do want to just spend the main topic of this talk, right, is we're trying to port associative memory to the modern era, and what I've just presented so far is just the toolkit. Like, what is the math that you need to be able to draw these connections? And so now I'm going to talk about some work we did where we did draw the connections. I'm going to assume that most people here are familiar with transformers, at least at a surface level. But I will go into just the bare minimum that you need in case you are not. So the conventional transformer, right, the thing that powers ChatGPT in the browser that you can talk to, that feels very human in the experiential and consciousness word, right, because it's very responsive and seems to understand, quote unquote, whatever that means. Its fundamental architecture is just this transformer block that has changed very little, honestly, since its conception in 2017 at the Vaswani All You Need. Attention is all you need. And this transformer block is composed of four main components, each of them a different color. It's got the multi-head attention, which is like the key signature thing of transformers. It's got the MLP in blue, it's a two-layer feed-forward network. It's got layer norm, which is just a way of turning your tokens to make them look like standard Gaussians that have been you can learn a scale and a shift, but just for the sake of this, layer norms are just turning tokens into standard Gaussians to look like as if they were drawn from standard Gaussians. And addition, this addition is skip connection, right? So a transformer will stack L of these. Capital L stands for number of layers, and its job is to take tokens at I call them XT. We'll talk about that. That's to make a point. At the input of the layer is XT, and the output is XT plus 1. Right, so you're going to transform tokens X into new tokens XT plus 1. But it's got some problems, right? So this whole block is designed through empirical success. We just stumbled upon it, and it happens to work so darn well. Where is the theory describing what these things are doing? Well, there are lots of opinions, and we have our own, but really, no one knows. Transformers are generally inefficient in the number of learnable parameters. Like, we know they keep getting better as we keep making them bigger, so let's keep making them bigger. People are arguing that we're kind of reaching the limit on how much we improve by making them bigger. It's possible, but I think that as we start to connect multimodal data, we will still benefit from bigger models. I think we'll see that. And finally, these giant models are relatively black box, difficult to interpret things. I started my whole career in AI just trying to interpret transformers. which turned out to be really fun because no one knew how to do it, and we had just some really simple and seemingly effective ideas early on. But these are real problems. This is just something we accidentally walked into. What's the theory? So what we tried to do, right, is I'm very familiar with transformer models, and Dima's very familiar with associative memories, and we had lots of conversations like, what's going on here? So this is the conventional transformer block shown again. And this is the transformer with L of them stacked together. X0 is your initial input, right? So in the context of GPT is, for those not familiar, it's like a next token predictor. Given some part of a sentence, it tries to predict the next token. Or like BERT models, maybe. Given a sentence where 50% or 10% to 20% of the words are missing, the whole transformer is going to try to fill in the missing words. Again, you can already kind of see connections to associative memory here. But there's one very important thing about this architecture and the way I've drawn it that I want to show. And that's this thing called the residual highway. Basically, starting from your initial input x, all the way to your output x star, in between every layer x1, xt plus 1, etc., there is skip connections all the way through. In literature, this is called the residual highway, and it looks a heck of a lot like a dynamical system. That is, xt plus 1 is equal to xt plus some function of xt. So our challenge after realizing this is like, how the heck can we turn this into an associative memory because it looks a lot like it? If we can define f to be the negative gradient of a real energy function. So that's what we set out to do in our paper, The Energy Transformer. We set out to find what this f could be such that f is the actual gradient of an energy function. Turns out you can't actually find an energy function for this configuration of the conventional block. But if we do some very small modifications to make it look like this, the energy transformer block, we can get an energy function for it. Note, this energy transformer block has the same 4 components from the conventional. We have the layer norm, we have a skip connection, we have the Hopfield network, before it was the MLP. Turns out the MLP is very similar to just a standard Hopfield network when you put a ReLU on top. Not enough time to dive into that in this talk. We'd love to talk more later. And what's novel in this work is we found the energy such that the derivative of it looks a lot like multi-head attention. So what's the benefits? We designed from theory first, right? We said we need to design something that defines a fixed point attractor. We need to define something that is a Lyapunov energy function. We know that this model is much more efficient in the number of parameters because in an information theoretic perspective, we're doing the best we can with this energy, right? We're recurrently applying it. Every parameter has a meaning. And so we don't have to have L separate layers of parameters. Now we just have one. We just recur it, like capital L times, to get the output. And because it's an associative memory, and remember how I talked about in the early classical Hopfield network dense associative memory regime, every row of that synaptic matrix is a data pattern we can visualize, we can do the exact same thing on something much more powerful, on something on the scale of transformers. We can look inside every parameter to interpret what they mean, because every parameter serves as some form of attractor in the energy transformer, which means it looks like data. So again, I'm writing the math here for those interested. I will not talk about this math. Just know this is the energy for attention. We use the log sum exp. What's special about the log sum exp? Well, if you take the derivative of it, it becomes the softmax, which is exactly what you use in the normal transformer for attention. Right? This was not our discovery. This is something that Ramsauer et al., Hopfield Networks is all you need, applied to transformers, but they did not capture the recurrence. There is no recurrent formulation in their paper at all. We do. We define an energy function that is a Lyapunov for attention. And we define a Hopfield network energy instead of the MLP. The total energy of our block is the sum of those two energies, just like the hierarchical framework we talked about before. These energies have intuitive meaning. Energy attention makes queries, query tokens, Q, look like key tokens in the latent space. The Hopfield network makes tokens look like the memory matrix, psi. The energy transformer does both. So empirically, what does this look like? We trained a vision transformer. On the left, the corrupted input. The right, the clean image. Again, these are images, but we did not train on these images. We train on a separate training set, right? We just want to know if energy transformer can generalize from that training set to real-looking images. And as you'll see as we descend the dynamics and descend the energy, I believe it does. We complete things like borders of cucumbers, non-trivial borders of cucumbers. We complete missing eye of dogs, and we start to complete the missing eye of dogs here. The question is how close we are to the fixed point. We complete boundaries. However, here's some things that it hasn't learned. It hasn't learned that bricks should be of a consistent shape. In fact, if it sees a line, it's just going to try to make that brick a really long brick, because that's its best guess for what belongs in those long, large missing patches. What else? I mentioned it's highly interpretable. HN stands for Hopfield Network. ATTN stands for attention. Early in the network, we pass in a corrupted image. Yes? I can see what the Hopfield network wants to turn this into, and I can see what attention wants to turn this into by just visualizing the gradient through the energy. That's what's shown here. That's the emphasis, just that you can see the structure of a dog in the attention. You see the Hopfield network is not really doing anything to the corrupted tokens early on in the model. As you go deeper in time, it's almost like the role switches. You're given most of the image. Attention's like, yeah, I've got all the information where it belongs. And Hopfield network's like, okay, great, I can make this look sharper. So it turns blurry patches into cleaner patches. What this looks like in the form of a video is as follows, right? The input is here. Let me go back so it goes fast. Corrupted input's here to one of the energy transformers at time t equals 0. We're going to take the layer and all of it looks the same. Nothing changes. We're going to compute what the gradient should be out of the attention and what the gradient should be out of the Hopfield network, and we're going to sum them together to get the total signal. Then the updated state is going to be this, skip connection on the outside, plus the signal equals the new token state. And we're going to do that for however many steps we trained it. We're going to do that for a bunch of different images just to see what happens. The Hopfield network has some behavior over time, the attention has some behavior over time, and this is going to converge to something that looks like a local minimum in the energy function. That's energy transformer. May I take a quick poll? I started quite late. I don't know what time I'm supposed to end.
Oh, I think you're fine for now.
Okay. I don't have much more. I just want to know how much time I have. So that's the transformer. Those are our empirical qualitative results to understanding how we can design transformers from the ground up to be interpretable, effective, to say what a transformer is doing. What if transformers are just error correctors? What if they're just trying to find the optimal configuration given their inputs? And I think that, in general, that is what they're trying to do. We've just described it in terms of classic associative memory. The next thing that we looked at, right, is diffusion models. And I honestly think the connection to diffusion models is much simpler than that of transformers. Again, it's a bit tricky to build up the full intuition for diffusion models in this talk, but I will try to do my best. I just don't have really great descriptive figures. The idea of a diffusion model is I want to learn a model such that I can remove any kind of noise added to an image. Or in this case, if you view an image as a dot, the dots should live. There's only 2 data points here, right? At the top right and lower left of an energy landscape. Some of these dots, I've added so much noise that they end up so far away. But the process of a diffusion model is to learn these gradients, that is, these arrows, such that I can push dots from far away to where they look like there's no more noise left. It is an error corrector, right? And of course, diffusion models are very noisy stochastic processes. The way it does this is by adding a bunch of noise every step to the gradient, and eventually you converge to a local minimum. They talk in probability, so it would be a local maximum of the log probability. The problem is diffusion models don't predict energy. They're not Lyapunov energy functions. They only predict energy gradients. In practice, you can see these models are incredibly effective, right? But they do this without any concept of a real energy. They just need to know the score function, which is defined as the negative gradient of the energy. Side by side, this is what associative memory looks like in the same paradigm as diffusion, right? If this first dot here is our corrupted signal, we're going to descend the energy, or ascend the log probability here. They're both the same, right? Energy is proportional to negative log probability to find a local minimum or a local maximum. We're going to just say energy. So they both find a local minimum of the energy function. The difference, right? Here's the difference. In diffusion models, I have a model, can be any model off the shelf, that returns, given an input, can spit out a gradient. It's a little bit of a lie. It can't be any model. What are the constraints on a diffusion model? A diffusion model must be a parameterized model that takes in some d-dimensional input and spits out a d-dimensional output, because that d-dimensional output has to represent the gradient with respect to that input. Right? We have to be able to perturb in data space this original input to look more like a real image or whatever the data is that you're modeling. So that's the only constraint on diffusion models. You don't actually have an energy. Associative memory is different, and that's emphasized in this plot here. Rather than these arrows, which are learned in diffusions, what I care about is the contours. I'm trying to learn the energy function itself, right? And there's a lot of ways to do that. There's contrastive methods. You can actually train associative memories using this score matching algorithm of diffusion models, right? At the end of the day, it's the energy function parameters you're learning. So you're just matching the gradient of the energy function to the arrows. You can learn it that way too. And then when it comes time to use diffusion models, like to generate an image, you have to initialize it with something. So people initialize it with noise. And then they descend from pure random noise to some local minima on the energy function. And that local minimum will represent the beautiful, looks like I was drawn from the data manifold image that you wanted ever to begin with. So yes, this paper, Memory in Plain Sight, workshop paper, it's on arXiv, y'all can read it. It's a very introductory thing to associative memory because so few people know about associative memory and how it works. And its primary claim is this, is that what people call the denoising process of diffusion models, it is just memory retrieval. Like that's the formal term for it from the literature of associative memory. It's just that the denoising process doesn't have a Lyapunov function. We just assume that the gradient exists or that our model has learned a good representation for the gradient. So given a noisy input, what can we say about diffusion models? We slowly remove noise until we converge to a memory. This process minimizes energy in forward time. And of course, you can read the paper for a few more details on diffusion models. Diffusion models are probably my favorite way of modeling in the mainstream AI. It is so close to associative memory, and honestly, to me, so close to being right. The only thing it's lacking is like a good theoretical understanding of the energy, which would allow us to characterize things like, say, the memory capacity of diffusion model. How do you characterize the memory capacity of diffusion model? It prevents us from doing things like contrastive learning inherently, like you can do with standard energy-based models. And it's a little confusing because the equations that you use to do this memory retrieval involve temperature annealing and step size modification, which in the paper I call kind of engineering tricks to make diffusion models work really well. Those engineering tricks would probably help make associative memories work well too, to be honest, but we haven't tried those yet. But the theory, right? The diffusion model theory is so tied up in those tricks when I believe that what's fundamentally happening is just a memory retrieval process. That's the case of that paper. So let's just conclude with, honestly, a quote from, there's no better way to conclude, a quote from John Hopfield himself from the talk that he gave at the Associative Memory Workshop at NeurIPS. He said the following: looking forward, I hope that the ideas of useful computation performed by physical systems will not only become helpful for interpreting the computational algorithms of existing AI architectures, I hope it will also inspire a new generation of AI networks that will have more computational properties, more powerful computational properties than current state-of-the-art models. Such a hope. Feel free to scan that QR code and give that talk a watch yourself. It is very motivational for me, as I do work on the new generation of AI networks. We'll give it our best shot. So there's a ton of things that are foundational to the works that I presented today. Here's a list. I can send the whole list with all the links to the chat if people would like that, the Colloquium chat, after this talk. I only worked on like 3 of these. Dima's worked on many in the recent years, but of course there's many other labs also starting to see connections here. I would call it contemporary with someone else who noticed something similar about diffusion models and associative memory. There's some language that I like to use taken from the Universal Hopfield Network formulation. Ram Sauer et al.'s Hopfield Networks is all you need. They honestly inspired me to step up my game to try to compete, right? So there's a lot of good work out there on this, and there's a lot of opportunities for research too. So yeah, Hopfield Networks 2.0. Certainly, we are in a new era for associative memory. My question to you all is, are we also in a new era for AI? That's TBD. That's why I'm doing my PhD. So thank you to you all for listening. Also, huge shout out, Dima, of course, many conversations to get my sad brain up to dynamical systems and energy functions and coding. Bao, who I collaborate with on many things, Hendrik, my mentor at IBM, and Paulo Chow, my advisor. Huge shout out to them. I hope this was interesting to you all. I'm open to whatever questions now.
Yeah, so I have a question, which is, again, I don't know how to phrase this exactly, but is any of this useful, right? Like insofar as like competing with like like standardized benchmarks and so on and so forth. like, what do you see kind of as a bottleneck to making these both more widely adopted? Not even so much because they're like theoretically interesting, but we can do X, Y, and Z with it.
No, these are that is central to my thought process almost every day. How do we get these models competitive? Because the theory says they should be, but me as one of the only coders and developers on trying to push this agenda has not been able to scale this to the level of foundation models or even BERT models from 2018 on language yet. I think that's probably the biggest thing is where is the workforce to help me out here? Because transformers, diffusion models, I would say that there's a few small armies working on those. And those small armies have people that are honestly much smarter than me and capable than me in many ways. So yeah, manpower, brain power, those are two that are blockers. Also, these models, they're not super well understood. Like, how do you train these models is also an open question, because what I described with the energy transformer, right, where you take an input and then you go down the energy function some capital L steps, and then you get some prediction, and then you do back propagation on your single layer parameter weights, right? What I've just described, that back propagation process, is also known as back propagation through time. And if you know anything about AI research, back propagation through time has this terrible side effect called vanishing and exploding gradients. So this naive way of training, even though it works really well for all of these other architectures that seem to have many different parameters across layers that can distribute the load of the gradients, whatever, seems to really struggle with our models. So it's hard to push state-of-the-art agendas when things are not yet fully understood how to do. Yeah, open research question. I really hope that one day they do compete in the state-of-the-art, and that's my goal. Yep.
Question. I was kind of wondering, kind of like when you're describing like the denoising process, how that sort of compares and fits in against like compression algorithms, because like you're kind of doing a similar sort of thing with the data, right?
Sorry, can you say that one more time? The denoising process is like a what?
It kind of like resembles like compression, so like compression algorithms and whatnot.
Compression.
Like if you have data and you can compress into a smaller format and then get it back, right?
Yes. Again, I am not going to be the most expert in answering this, but I'll give you my best stab. So let's consider the two-layer case. Two-layer case. Let's consider the case of a dense associative memory where you have some visible neurons, right, that represents your data, and then you have some latent, just one latent, and you have one weight matrix connecting those two. I take my input and I project it into the latent, the hidden, the quote unquote compressed representation through this weight matrix, right? And then I can carry that around to represent the data. I don't need to represent all the giant, 100,000 per long pixels that I stored in my memory. I just need to carry around the latent, because once I have that latent, then I can just decode that latent. So long as I have the original weight matrix that encoded it, I just take the transpose and I'm back to the original data. Following the energy dynamics. So there is a connection to compression, absolutely a connection to compression. And beta is not a parameter, it is a hyperparameter. So technically, what we get out of the decompression that is following the memory retrieval from whatever we've stored, what we get out of it is dependent on what we choose for beta. We can get out many different things depending on what we choose.
Thanks.
No, it's a good question. Compression in these things is also an open research topic. Can you see my agenda of trying to encourage people to work on it? More questions?
I have a question. So,
go for it. I think I can hear you over him.
So, it was kind of funny that you mentioned back propagation through time a moment ago, because I wanted to ask this in the talk. But so I'm very interested in alternatives to back propagation, and that seems like it would be sort of a way forward. In that, if back propagation through time, in addition to like vanishing and exploding gradients, it also, like, by choosing a time cutoff, like if you're doing truncation, or if you're doing a let's say like you just have like a natural like fixed length you go to, it can introduce artifacts that way. So I was wondering if you thought about alternatives to back propagation as well for training.
Yeah, you mentioned Hebbian. That was you, right?
Yes, that was me. Yeah.
Okay, yeah. We've tried. I can't say that I've tried at scale. I've tried on simple data sets. I've tried in the classical Hopfield and the dense associative memory regime. Works great. Of course, we're not competing with state of the art in that regime. And energy transformer seems to have a little bit more trouble training that way, just because I think the system is a little more complex. The data is more complex that we want to scale to. But I'm sure it's possible. And it's something that we're actively working on, alternative training for this stuff. If you have a favorite, feel free to ping me at some time. We can try it quickly. The goal is to try to get something off the ground as soon as possible to make these things scale. And I think a new training algorithm is necessary. Yeah.
Thank you.
Do we have more questions?
TM you a paper you might like.
Sorry, may I have a question? It might be a little bit dumb, but can you explain maybe if it's possible to work with time series data with Hopfield networks, so like sequential data?
Yeah, so my expertise is certainly in the architecture design. Mapping architecture design. I will say that energy functions are really nice because you can design them such that they do the job that you want. Which means that you can intuitively make like synapses talk to. I only want a convolution to attract me to the last 3 time positions or something. I don't know. But anything that a transformer can work on, that was kind of a big thing for me to see with energy transformer. Anything that a transformer can do, which means that if a transformer can do time series, an associative memory can do. Because we think that the two are basically doing the same thing. Actually getting it to work is also a big challenge, though, because you have to encode the time series in a meaningful way, or I guess in the words of transformers, you have to tokenize it in a meaningful way. And that's out of my area of expertise.
Okay, so for example, can we work with maybe video like sequence of images? So you show here the nice work with reconstruction of images, but if it will be like going like a video like sequence of frames, something.
Actually, I'm gonna strengthen my previous statement. So in this talk, we've drawn connections to both transformers and diffusion. And I have on Twitter not that often, but enough to see like state-of-the-art video generation models be published, right? What are those things? They're diffusion models, right? They're diffusion models that are able to diffuse through time. And if diffusion models can do it, we can find a way to make associative memories do it. Might be trickier, and we might be shooting ourselves in the foot because we're tying ourselves to a theoretical framework, right? Like we can't just use any like unit off the shelf. We have to design a special unit, and we have to see if that works. But yeah, if a diffusion model can do it and a transformer can do it, we can do it.
Okay, thank you.
Got more questions?
All right. Thank you, Ben.
Yeah, thank you so much. Those are really,
Yeah, this was amazing.
Okay, great.
yeah, that was
I
a really
glad
great
to be here.
presentation.
Thanks a ton, y'all. I made it starting at 6 a.m. this morning, so don't encourage me. I need to do it in advance next time. All right, but I'm going to sign off and grab some dinner. Thanks, y'all.